In lesson 10, we'll take a look at a CAN issue on a John Deere S660 combine. This machine had complaints of intermittent engine speed surge or engine speed drop to low idle. This was a very intermittent issue. As I recall, the tech had started working on this machine the previous harvest season, so last year, and because the machines in this area, combines are only used a month or two out of the year, he wasn't able to fix the issue the previous year or find the cause of it the previous year. So this year we took a look at it using the picoscope. We were able eventually to capture the issue. I actually rode around in this machine for an entire day with the customer and with the technician, and it was flawless. We never had the problem. We tried shaking the wire harness and moving components and tapping on things, and nothing occurred. Unfortunately, a day or two later, the technician, we were able to actually capture this issue occurring on the machine. So here's the waveform, what that waveform looked like. We can see that looking at this, first off, this is a 250K actively terminated network. We can see that at some point it looks like we have a problem with CAN high. We don't know, is this one single controller at this time, or is this multiple controllers? In other words, is this a problem with the stub, if you would, that comes off of the backbone that goes to the controller? A connection at the controller, some problem internally with the controller, or is this a problem with the backbone where we've got an intermittent open circuit someplace? And so in order to be able to get to determine or to help us pinpoint where the problem is, we need to be able to obviously decode this waveform. If I look, we can see that there are times that messages are going through. Obviously, they look fine. We can see by the acknowledge bit that at least this message went through. We can see at another time that this message apparently got stepped on by this problem that we have with the machine. Other times the waveforms look fine. We can see that there are these periods where it looks like we have good waveforms. We can see that there doesn't appear to be a problem. If I go ahead and take a look, I'm going to change the voltage here to help this make it a little clearer. We can see that at some points it looks like we have places where the first couple of bytes are elevated in amplitude, and we know now that this is actually arbitration. So this is an instance, this isn't a problem, this is an instance where this controller started transmitting, somebody else or another controller, at least one more controller than it, started transmitting. We can tell by that difference in amplitude, and it lost arbitration. And so those controllers went into, as we spoke, they just went into a receive mode, just stayed recessive, while the controller that won arbitration continued to transmit. We can probably see that's going to occur a few times in this. So when we see those waveforms, and those we probably have several in this packet, we don't worry about what we see for those first few bytes of data, like this case. This isn't a problem. This is just arbitration. And of course, at the end, we have the acknowledge bit. So the amplitude of this is multiple controllers. Here you can see one that lost arbitration very quickly. And so we had more than one controller here with the start of frame bit, and then it lost. So we're not worried about patterns that look like this. We're more worried about patterns that look like this. This will be one of those things that it takes some getting used to with the oscilloscope. What's a problem and what's not a problem? So just knowing and looking at this message, I can see that there may have been one or more controllers that was able to partially decode this message, and they did not agree with the message that they saw. And we can tell that by the length of this time after the acknowledge bit. We can see that this is what we call an error frame, and we'll talk more about error frames at some point. But this is a CAN error, not a DTC necessarily, but a CAN error. So what I need to do is I need to try to decode this. And if I use my if I take my math channel and I use my A minus B, or I use my homemade math channel, the one that I use a lot, CAN high minus CAN low, just so I remember that A is CAN high, B is CAN low. You can make these math channels yourself. You can put whatever names you want in them. If you have the labels, you can change the labels of the channels. I do it pretty much with these videos so that we know what it is. But here I've got a math channel that I'm actually going to create a new math channel. And what I want is a math channel that is going to take, I want to try to turn this into a waveform so we can see that on CAN low, it drops down to about 1.25 volts, and on CAN high, or excuse me, on the recessive bit, CAN low stays at about 2.5 volts. So what I want is a 0 and approximately 1 volt signal. I want a digital signal. So to do that, I'm going to create a mat channel. So the mat channel is going to be, I'm going to try 2.5 volts. I'm going to subtract B from that. And so this is going to be my mat channel. We'll make it pink so that we know that it looks a little different. And that should look good. Let's go ahead and finish. Okay, so now that I've got this digital signal, I can create a serial decoder. So I'm going to go ahead and pick CAN J1939. We're going to go with the 2.5 volts. We're going to change the threshold. Let's go with about 800 millivolts or 0.8 volts. Hysteresis is fine. And we're going to go with 250K. So this is a 250K CAN bus. Go to hex, and there we go. So right away, I can see that it looks like it's decoded this message, but it didn't decode this one. Let's go ahead and modify. The great thing is we can modify this. We'll change this down to about 0.7. Let's change this down to about 300 millivolts. And we'll go ahead and finish. The decoder doesn't cost anything to go in and modify the decoder. Rarely are you going to get it right the first time. So we can see here in this case, it looks like my device that has the problem might be this source address D3 in hex, whatever that is. We can see, as I told you before, definitely this is an error frame out at the end. It's not happy. Some of the controllers are not happy. We can see that we have other controllers. It looks like repetitively what I'm seeing is what I'm finding is that source address D3 appears to be my problem. We can see here it is again, D3. We can see other ones are trying to communicate. Sometimes they're able to get a message through. Looks like this was not able to decode. It looks like the amplitude of this is a bit lower than that, so we weren't able to get that message. But I think we're able to see for the most part that my problem controller is probably going to be this device D3. We need to I'm going to get several examples of this. What you're going to find is when we have a problem with the backbone someplace, in other words, out in the harness between CAN high and CAN low at a connector someplace, not necessarily at a controller, what we're going to see is we'll have multiple controllers that will have this problem. So in this case, I'm pretty sure that my problem was this controller D3. So what is D3 in decimal? Well, of course, I can change the decoder to be in decimal, or I can use the Windows calculator. So in hex, I can put in D3, and we can see that that is source address 211. From this, I was able to use the John Deere has their tool, the Canon Connectivity Health Wizard, the controller information tab. From it, I was able to find that source address D3 is something that John Deere calls the AYM in their device, or TLA. What this is a product moisture controller. So this is a controller that's on the CAN network that's able to find or determine the moisture that's in the product. So in this case, we changed the product moisture controller. And the great thing about working on a combine is because we didn't actually find this until the end of the season and the customer was done working in the field. We've replaced that product moisture controller. Obviously, we can start it and run it and let it sit at idle or run at high idle and tap around on the harness and everything else that we did while we were trying to diagnose the problem and couldn't usually recreate it. We assumed that we probably fixed it with this controller because, as I said, we won't know for sure until next year. Yes, I do have a bet in with one of the technicians regarding an adult beverage to that, so I'm pretty sure that I'm going to win that bet. I'll also indicate that we did also replace the terminals at this controller. So this is has the quad CAN, so we have the power, ground, and CAN high and CAN low all in the connector. So there's a small harness section that breaks out a short 6 inches or so. So the tech did cut those and splice in new terminals into that, just in case it was something with the terminals, even though the fit showed that that wasn't the case. We assumed that this was a problem within that controller, within the driver for CAN high for this. Probably took a combination of heat and vibration in order for this to be able to manifest itself. As I said, I guess we'll see next year whether this fixed it. I'm pretty sure it did. Okay, so here's a completely different machine. This is a John Deere 9510R. This is a 500K actively terminated CAN network. So this is a John Deere tractor. The complaints on this one were that the engine would start and die after 5 seconds or so. Some other times it would die intermittently. I guess after running for a period of time, it would set a DTC that indicated we had a problem with something called the immobilizer. The immobilizer on John Deere machines is basically it's indicating that you didn't use the right key to start it with. So I believe all the John Deere machines are pretty much keyed the same on the lock cylinders for the ignition. The difference is there are, at least for sure in Europe, and it is an option, I believe, here in the States, you can get a different colored key. So instead of a red key, it'd be a green key. And within this green key, there is the same thing like your automotive. There's an RF tag that's inside of it. And so it's able to read that to controller and verify that you have the right key for this machine. So that is the unique piece of it. It's to keep somebody from being able to steal your tractor just because they have a key for it. So even though these machines in the States do not have the immobilizer, it's still within the software of the engine controller. So the way that works is you put in a red key and it doesn't have a mobilizer, you start it, and if that CAN messages cannot get through from that, typically, I believe probably the EIC, the engine interface controller, maybe a different controller, I'm not sure, but it would send a message to the engine controller telling it it's okay to run. If the engine controller doesn't get that message within 5 seconds or so, it shuts down and it sets the fault that's like you're starting this and you're not authorized. So it's the immobilizer. So if we have a CAN problem on the machine that causes a lot of issues right after we start it, we'll set that fault and we'll shut the engine down. The crazy thing was that this would, if he left the machine set to where it had sunshine on the cab and it would heat up. So this apparently was something that started here recently as it got cold. That alone would cause this to no longer happen. So it may, after the sun set on the cab for a period of time, it'd be all good and he'd start it and run it and wouldn't have the problem. So we were, obviously we got this machine when it was cold and it didn't have the problem. Eventually it was able to manifest itself. It's kind of weird how these things happen, right? You're watching it and trying to create the problem, and of course everything works fine. But here we can see that we definitely had an issue. Something occurred on the CAN bus. So what we ended up doing with this, I ended up wanting to decode this. So my math channel that I used for this instance, because I have a problem with CAN low, I'm using A, which is CAN high, minus 2.5. So what that's going to gain me is a somewhat digital looking waveform. This looks kind of ugly, but it's able to do the trick. The other thing that I did with the decoder is that I dropped it down to a pretty low amplitude, so half of a volt. And if we look and see, I have that set to basically 0.5 volts. We can look and see that if I pull this down to where it's somewhere near 0.5 volts, I'm getting a pretty good digital signal out of that. And that's what I was looking for. So it's not perfect, but it's good enough for me to decode and figure out who the problem is. So here we can see that source address 36 hex appears to be a problem. Over here, 22 is not. I don't know what that one is. There's 36 again. Here's 37. So in this case, what I'm trying to do is to determine, is this a single controller or is this multiple controllers that have this problem? I can see that it appears that source address 36, which in this case happens to be 54 in decimal, that is something that Deere calls the ASU. So this is the seat control is what it's described as. So without going into a lot of detail, so I wasn't sure exactly where the seat controller was located. We looked on the schematic and we tried to find something called the seat controller. And of course, there's not a device or a controller on its own that's called the seat controller. And so it took quite a while, but we were actually able to determine that the seat controller is physically, it's what's called a controller application. So this is where it really gets fun with J1939, and especially working on ag equipment. One single controller, one physical box, might have multiple what we call controller applications within it. And so each of those controller applications is basically a piece of software. The device has one CAN transceiver. So the physical hardware, there's two pins that go to it, has power and ground. It's a controller, and contained within that electronic controller are all these pieces of software. So this ASU is one of those pieces of software, and it claims an address. Other controller applications are contained within that one. So this was kind of tough to figure out. It took us a while to figure that out. But one of the things they're able to do, one of the things you can do is we can see that this message is not getting an acknowledge. So if I sort with down below here by acknowledge, who is getting an acknowledge or not? And it looks like every time the controller that is not getting an acknowledge, meaning the other devices are not detecting it, is source address 36. Here's kind of an outlier. Let's take a look at it. And the reason that 22 hex in this case doesn't have an acknowledge from the other controllers is it's in that gap between waveforms. So this controller, the message did not finish. So this would have probably been okay. It appears that this message is fine. The problem is this is one of those things. Sorry, Pico, I don't like this about the scope. If it doesn't get the entire waveform or the entire message, it tries to decode on the partial message and then throws basically an error and says, there's a problem with this. This is one of those things you got to watch out for. But we can see here for the most part, it's typically that 36. Here's another example. This is 31. It's right at the end. It did not get to finish the message. So this is one of those pitfalls you got to be very careful of. You learn the equipment. Hopefully one of these days Pico will take care of this. If they watch these, I'd like to see them not try to decode a partial message. They know that it's a partial message. It's the first or the last message. Let's flag it that this is definitely maybe not an error. But in this case, we can see that it's typically always source address 36. Here's one again with 13, but where we really have the problem we can see is source address 36. So it's easy to say this is probably our issue. It's not any other device on the network, but it is definitely this seek controller. And you can see that obviously this wouldn't be a message that would be broadcast quite frequently, but because this device cannot get the message out, it can't get an acknowledge, it is pretty much destroying the CAN bus. We can see here that it's interrupting traffic. It's causing, obviously this is an error frame based on the width. This is something that we need to fix, right? Okay, this is our issue. In this case, I'll go ahead and open up another waveform that I captured from this because it's slightly different from this one, even though it's the same machine. Okay, so this is this same tractor, and in this time we took I believe this is the first instance of when we captured the data. We can see that this time it appears that source address 6 in hex, which is 6 in decimal, the engine interface controller is the device that has our problem. Obviously, I believe this is the controller that has to send that authentication message to indicate that we have the right key to permit the immobilizer to let the engine to run. We can see here now instead of 36, we're repeatedly getting source address 6 as our problem. This is one of the challenges with especially maybe some of these older John Deere machines. They seem to do a lot better job of it now. It's really hard to determine which physical device can change this source address 6, or the EIC, as Deere calls it, the engine interface controller. So once again, using John Deere's Canon Connectivity Health Wizard, in the controller information, they have something called controller details. And in that, using that controller details, it lets you determine which of these devices, these TLAs, source addresses, are in a particular piece of hardware. And using that, we were able to determine that the device that contains the EIC, that contains the ASU, that source address 36 in hex that we were looking at, and source address 6, is the cab controller. we were able to go to the cab controller. We know our problem appears to be one where we have an issue with CAN low. And at the cab controller, sure enough, it was kind of suspicious. The zip ties to the controller around the controller were cut, had been opened. Someone had been working on this at some point. We went to the cab controller. It uses the cinch terminals. If you guys know the Deer Techs, definitely know what those are. You need the little two-wire removal tool. It's the same thing that the earlier John Deere engine control units, ECUs, use. So like a level 14 ECU, for example, 15. It's that type of connector. So we were able to extract the terminal for CAN low. We use the John Deere, they have a part number, a special part number for the what they call flex probe. So to be able to test the terminal fit to see how tight it is. We put that terminal in it, turn it upside down, and it falls out. So that CAN low terminal on this machine was spread. CAN high was tight, as we can see here, but CAN low was spread. And sure enough, someone had worked on this in the past. I don't know how long ago, but they had worked on this. There had apparently been a problem, and they were trying to diagnose a problem, I assume. And in so doing, they probably spread those terminals. And so this appears to be another one of these self-inflicted problems that come down the road from having used the wrong terminals or trying to use my test leads from my multimeter and to jam those down in the connector. We were able to replace the terminals on this, replace those cinch terminals, and it looks like it's taking care of the problem. Once again, this was fairly recently, so we'll have to give it back to the customer, but we could not duplicate this issue again. We actually reached a point where we could wiggle the harness just right and hold it just right and get our problem to occur. So after we replaced those terminals, that issue went away. So this is an instance. I don't know what those terminals cost. I suppose they're, even at John Deere, only a couple of dollars a piece. Obviously, the labor and getting the machine to the dealership and those kind of things are a lot more expense. But for the customer, this is a relatively inexpensive repair, and we were able to find this using the scope data. And maybe one other thing to mention, as you can see, this doesn't look, even though this ended up being an open on CAN low, we can see that the waveform doesn't actually look for the CAN high. It is not our nice sharp corners that we're used to. So apparently this is, I really don't have a great explanation. Maybe somebody who's a better engineer than I am can explain that. We may be getting into a region where we're actually resistive and not necessarily open, if that makes sense. So it's not a true open circuit. It's a very high resistance circuit. So I'm going to say that's why these rise times on this are long. It's kind of a mystery to me. I don't have a great answer for that. All I know is sometimes you have these open circuits on CAN and you get this pattern, and we'll see that for sure in some later instances where I know that we had a resistive issue. But when you see this pattern, don't be alarmed that it's not a nice clean rise time. As I said, this is CAN high. Our issue was with CAN low. I believe that we probably reached a point where we were resistive and we're actually changing the impedance on the bus. That's my story, and I'm sticking to it. So next, we'll take a look at some other types of failures. We've seen quite a few here. We'll look at some where we have failures on passively terminated CAN networks, and then we'll get into some issues where we have multiple controllers. That makes it a little more difficult.